Hi, I'm Professor Goins. In this video, I'm going to look at finding tangent planes to surfaces in 3 space. All right, so again, a tangent plane at a point P on a surface is the best approximation with a plane for that surface at that point. Sort of like a tangent line, where like a tangent line was the best linear approximation to a graph, or the best straight line approximation to the graph at the point of tangency. So I want to go through and figure out how could we actually find the equation of that, do some specific examples. Recall when we talked about equations of planes before, we needed a couple of things. I need a fixed point P, so that's given by ABC. Generally, letters at the beginning of the alphabet refer to fixed constants. Letters at the end of the alphabet are variables. So I've got this point P, which is fixed, that I know is in the plane, and then I've got this normal vector N, and then I've got Q, which is an arbitrary point. Now, in order for Q to be a point in the plane, what has to happen is the vector from Q to P, or from P to Q, the vector that's between those has to be orthogonal to the vector N. That means if I take the vector from P to Q, I take the dot product with N, that should equal to 0. So this right here is the equation of the plane. Again, if x, y, z satisfies this equation, then it lies in the plane, and therefore this equation here represents the entire plane. All right, the surfaces we are going to look at can be written in a couple different ways, but they have to be boiled down to a level surface. A level surface is a function f of x, y, z equal to a constant. Here's a few examples. 1, x squared plus y squared plus z squared equals 1. In this particular case, this expression here is your f of x, y, z, and the graph of this is the unit sphere, so the sphere with radius 1 centered on the origin. Another thing I could look at is, well, what if I have a function? So this looks sort of like it could be maybe the graph of a function, z equals f of x, y. In particular, I could say z is x squared y minus 5y, so this would be a function of 2 variables. Well, if I want to turn this into a level surface, I have to have x, y, z all on the same side. So I'll simply subtract z over, set that equal to 0, and this equation right here would be of a level surface. So I've got this expression here, which is in terms of x, y, and z, set equal to a constant. Again, if I have an equation of like a sphere or an ellipsoid or something like that, then that expression in x, y's, and z's would be your f of x, y, z. If I have a function, I can turn it into a level surface by just setting it all equal to 0, or equivalently, if I had, let's say I made this a minus 3, and then I just add 3 to the other side, and then that would make that the function, or f of x, y, z is equal to 3. I just need to have f, x, y, z's on one side, and at most a constant on the other. All right, so we can work with either one of these, and I'll do an example of each one. All right, so now for the tangent plane. Well, the point P for the tangent plane is going to be this point of tangency, so it's going to be that fixed point right there. What about Q? Well, Q is going to be an arbitrary point, x, y, z, so that can lie anywhere inside the plane. And then the normal vector n is the gradient of the function f evaluated at the point of tangency. So our gradient vector is normal to the surface, and hence is also normal to the plane. So the gradient vector at f evaluated at p. And I started to write up an example up here, but I probably should write the equation of a tangent plane. So the equation of a tangent plane, I'll put that up here, so it's poor planning on my part, but anyway, the equation of a tangent plane follows this exact same format. It's going to be p, the vector p to q dotted with n. So in other words, it's going to be, just a different color here, it's going to be the vector p to q dotted with the gradient of f set equal to 0. Okay, so let's go through an example to figure out how that will work. Okay, so solution. In this case, I'm looking at the tangent plane to the sphere centered on the origin of radius 2. Remember that your f of x, y, z in this case is given by x squared plus y squared plus z squared. So in other words, our level surface is that function is equal to 4. All right, so there's a couple things I have to do here. One, I have to compute the gradient. So the gradient of this function would be 2x plus 2y plus 2z. And then I have to evaluate the gradient at the point of tangency. So let me do that up over here. Let me clean the whiteboard and give myself some space. So the gradient of the function f evaluated at the point P is 2 times the x coordinate, which is -1, plus 2 times the y coordinate, which is +1, plus 2 times the z coordinate, which is √2. So I've got -2 plus 2 plus 2 √2. So therefore, the gradient at that point is 2 √2. Let's see. Oh, one correction. This is the vector. So this is the vector -2, 2, 2 √2. Okay, sorry about that. That's the gradient is a vector. It's a normal vector at that point. So I do evaluate it, but again, it's the vector components. Okay, so there's the gradient of the function at the point. And if I go down here again, let me correct that down here. That is the vector with those components, 2x, 2y, d, 2z. Sorry about that. Okay, so then I'm going to go to the equation of the tangent plane. So that would be the vector p to q dotted with the gradient at p, and the vector p to q. So p is going to be this fixed point here. That's the point of tangency. Remember, q is an arbitrary point, x, y, z. And when we go to the vector p to q, it's final minus initial. So in other words, this would be x minus -1, y minus 1, z minus √2. And I take the dot product with -2, 2, 2 √2, and I set that equal to 0. So I take the dot product of those and multiply corresponding components. So remember, this is going to be x plus 1. I multiply that by -2. So I would have -2 times x plus 1 plus 2 times y minus 1 plus 2 √2 times z minus √2, and that's equal to 0. So let's clean this up then. I have -2x minus 2 plus 2y minus 2 plus 2 √2z minus 2 √2 and √2 would give you, so √2 and √2 is 2, so it's -4 equal to 0. So then I can just take the constants on the other side, giving me -2x plus 2y plus 2 √2z is equal to, so the constants out of the -2, -2, and a -4, giving me an 8. And I could leave it like that, or since all of those are multiples of 2, I could clean it up by dividing by 2 and get -x plus y plus √2z is equal to 4. So this would be the equation of that tangent plane. All right, the next example I want to work through is something similar to this one, where I've got a function of xy, so z is equal to a function of xy, so it's a graph in 3 space. and we'll have to convert it to a level surface. So let me clean this up and set that exercise. For example, let's say I have the function z is equal to xy plus 2x cubed minus 5y, and I'm looking at the point of tangency on the graph of 1, 3, and -10. So what I want to do is, again, find the tangent plane to the graph of this function at this particular point. Okay, so let's see how that works. All right, what I have to do is start with my function f of xy. To get the function f of xy, I have to turn this function notation here into a level curve or a level surface, and that would be xy plus 2x cubed minus 5y minus z is equal to 0. This then, of course, is my f of xy. F of xyz. And that's what I'll take the gradient of. So the gradient of that function, okay, the first component is the partial derivative of f with respect to x. That would be y plus 6x squared. The partial of f with respect to y would be x minus 5. The partial of f with respect to z would be -1. And then I have to evaluate that at the point of tangency. So the gradient of the function evaluated at p. Okay, so I take the components of p, 1, 3, -10, and I plug those into the gradient. So that would give you 3 plus 6 times 1 squared. X minus 5 would be 1 minus 5 minus 1. And that would give me 1 squared is 1, 6 and 1 is 9, 3 and 6. I'm sorry, 1 squared is 1, 6 and 1 is 6, 3 and 6 is 9, and then -4 and -1. So there's the gradient of the function at the point P. All right, and then finally I have to take the dot product, right? Because in order for an arbitrary point to lie in this corresponding tangent plane, the vector from xyz, which is a point in the plane, to this point P must be normal to, or orthogonal to this vector here. So I have to take the dot product, set it equal to 0. So that would give me the vector x minus 1, y minus 3, z minus -10, and then I take the dot product with the gradient, so 9, -4, -1, and again that has to equal 0. So we go ahead and multiply that out. I would get 9 times x minus 1 minus 4 times y minus 3. And then I have -1 times z plus 10. Set that equal to 0. And let's distribute and combine like terms. So 9x minus 9 minus 4y plus 12 minus z minus 10 equals 0. And then I'll leave the variable terms on the left and put the constant terms on the right, giving me 9x minus 4y minus z is equal to, okay, so what do we have here? I've got a 12 and a minus 10, so that'd give me a positive 2, meaning over here I'd get a negative 2. So this right here would be the equation of the plane tangent to the graph of that function at the particular point p is 1, 3, negative 10.